So, welcome everyone to the Atto Fridays. It's a pleasure today to have Dr. Lidice Cruz Rodriguez as a speaker. You have seen her some years ago on the other side because she used to help us run this show. But it's really nice that today she is the star of the talk. Dr. Lidice Cruz Rodriguez has completed her PhD in physics between the University of Havana, Cuba, and the University Paul Sabatier in France in 2018. Her PhD focused on developing trajectory-based methods for quantum dynamics, exploiting the Bohmian formulation of quantum mechanics. Before she moved to the UK in 2021, she was an assistant professor at the Faculty of Physics at the University of Havana, and she started her first postdoc at UCL, in my group, in fact, in 2021, where she focused on developing forward path integral methods for photoelectron holography and applications in strong field physics. And she's currently a research fellow in the group of Professor Scott Haberstone at the University of Warwick, working on novel Gaussian wave packet methods for quantum dynamic simulations as part of the Cosmos project. But I'm going to use also the opportunity to say that she has been working on Bohmian trajectories for a long time, and this is in fact her field of research and her research line that she has been developing independently. So do watch her talk because I'm sure you're going to learn a lot. And the floor is yours. We're ready to go, and we are all ears. Welcome to the Atto Fridays, Lidice.
Thank you, Carla. Thank you very much for the nice introduction. Let me share my screen and check again. Okay. So as Carla said, I'm going to talk today about trajectory-based methods for ultrafast quantum dynamics, which is essentially what I have been doing since I started my PhD and through my 2 postdocs in the UK. I had a first slide showing my trajectory, which Carla described very nicely because it was is essentially my biography. So I come from Cuba, and I will not repeat all the introduction that Carla said. I moved to UCL for my first postdoc in 2021, and now I'm in Warwick in the group of Professor Scott Haberstone. And since my PhD up to now, I have been working on developing trajectory-based methods for quantum dynamics using different approaches, which are the ones I hope to present to you here today. And I always like to start my presentations with this very nice picture from this paper from Ferenckraut and Misha Ivanov, where they showed the length and time scales for structure and dynamics in the microcosm. And probably to this community, I don't need to bring the relevance of why do we want to look at the attosecond time scale, because we know it's the time that takes the electron to move inside atoms. And the developments in attosecond science has allowed us to actually take movies of this electronic distribution as they move in real time in atoms. And this was recognized by the Nobel Prize in Physics in 2023. Attosecond science is very related to strong fields. And I want to, usually I like to describe what do we mean by strong fields in case if we are not familiar with that. We say that the external field is strong enough when the intensity of the field is the order higher than the atomic unit of intensity. And from the theoretical point of view, this means we can no longer use perturbation theory to deal with the dynamics. And as a simplified picture, if we have a linearly polarized field in the dipole approximation, and we have an atomic model potential, and we have now this strong field interacting with the atom, what we see, the picture we have, is the following. So now this field is going to oscillate and move following the time-dependent field. And we have different mechanisms for, or many things can happen when we have this strong field interacting with the atom. And one of these phenomena, it's the higher the harmonic generation, that's the one that led to the development of the first attosecond pulses. So if we look at this simplified picture of the phenomena I want to describe, we have an electron that can be ionized because of this a high intensity field. And then what happens after the electron is ionized? We can have one scenario in which at the next cycle of the field, the electron can come back to the ion, and it can be backscatter, and then we have the emission of a high energy electron, or while the electron is being driven back, it doesn't see the ion anymore, but then it's free with a non-zero kinetic energy. We can have another scenario in which the electron can recombine with the ion, and it leads to the emission of a higher energetic photon, and this is precisely the high harmonics. Or if we consider the several electrons, we can have the detachment of another electron, and this can lead to non-sequential or sequential double ionization. In the problems I'm going to describe here today, I'm going to focus on, I have a single active electron, so I will not have double ionization, and we can have either that this electron, once it's ionized, it can move freely in the continuum, or it can backscatter from the core. So from the theoretical point of view, what do we need to do if we want to study or to model such phenomena? So this is a quantum mechanical problem. So in principle, we should solve the time-dependent Schrödinger equation that describes the propagation of this electron in the presence of these very strong fields. And we can think about the methods to solve the quantum dynamics, like divided in two big groups. We have on one side what we call the conventional methods for quantum dynamics, that methods based on grids or basis functions, but these methods, they are limited because the computational cost increases exponentially as the number of degrees of freedom increases. And this restricts the calculations to very to little amount of atoms. But on the bright side, this is an exact quantum dynamics description. On the opposite side, on the other side of another kind of methods, we have trajectory-based methods. They have the advantage that they offer a better scaling in general with system dimensionality. And also, by having a trajectory mapping of the quantum dynamics, we can gain a better visualization and understanding of the dynamics. But depending on the method, it might be challenging to capture intrinsic quantum effects like tunneling ionization or zero-point energy effects, because in general, we have kind of semi-classical description. However, trajectory-based methods are a very active field of research because of the better scalability properties that they offer, because even though we cannot capture sometimes quantum effects, they can show accurate results in many areas. And today I want to present to you some of the trajectory-based methods I have been working on since I started my PhD up to now. So I'm going to divide my talk in three parts. The first part, I'm going to talk about Bohmian mechanics and how we can use quantum trajectories to describe laser-driven electron dynamics. Then I'm going to talk about path integral methods for strong field ionization, and finally about Gaussian wave packets for nuclear dynamics. In this last part, I'm not going to talk explicitly about time-dependent fields, but hopefully by the end of my talk, you will understand why I'm bringing this method also into the table. So let's start with the first method, Bohmian mechanics for strong field ionization. And for those of you that are not familiar with Bohmian mechanics, I thought I will do a quick introduction. So just one word about Bohmian mechanics. It's besides the interpretation of Bohmian mechanics, we can see it as a tool to solve the time-dependent Schrödinger equation. And the starting point is that we have the time-dependent Schrödinger equation to describe the electron dynamics. This can be the electronic wave function. And then we need to introduce an ansatz in this form. This is the amplitude or the density and the phase. And then we can substitute this ansatz into the time-dependent Schrödinger equation, and we obtain what is the hydrodynamic equations. And if we look at these equations, this first equation is like a continuity equation and tells us about the conservation of the probability density. And these two equations here, we know them from classical mechanics. So this is like the Hamilton-Jacobi equation, and this one is a Newton-like equation. But because the way we derive these equations by starting from the time-dependent Schrödinger equation, there is a new term here that appears in these equations. And because it enters the equations as a potential, this is known as the quantum potential, because it's the one that brings all the quantum effects and is a source of non-locality in the dynamics. And if you look at the form of this quantum potential, you can see it depends on the probability density. So this means if we now propagate trajectories that follow these equations of motion, these trajectories will not be independent. Each of them will feel the interaction with the others through this quantum potential. So this equation here is like a Newton-like equation. And again, the quantum potential enters here. We have the gradient of this quantum potential will be like a quantum force. So in principle, solving this set of equations is fully equivalent to solving the time-dependent Schrödinger equation. And one of the ways of implementing the Bohmian mechanics, or the hydrodynamic formulation of quantum mechanics from the numerical point of view, is something known as the quantum trajectory method. And the idea is that now we have an initial wave packet, and we represent these wave packets in a discretized form in terms of n fluid elements. And each of these fluid elements, now this will be like a trajectory propagating, and each of them will have a phase and a density that they will carry along during the dynamics. Then we can solve this set of equations. And because we have an equation for the probability density and the phase along the dynamics, once we solve for the trajectories, we can know the wave function, and we can know any quantum observable we will want to obtain. But unfortunately, solving these equations is very challenging from the numerical point of view, and the most well-known challenges come from the fact that if you look at the quantum potential, the density in the denominator says that every time we have nodes in the wave function, this quantum potential diverges, and this makes the equation of motion extremely difficult to solve. Additionally, we need derivative of the hydrodynamic fields along each of these trajectories. And even though if we start with a uniform grid, a very well-structured grid, as the dynamics evolves, these trajectories, they become a very unstructured grid, and then the derivative evaluation is very challenging as well. So for the people working in Bohmian dynamics, they have come up with several numerical strategies to deal with these challenges. In my work, I have used two different approaches, either polynomial interpolation or finding analytical approximations for the quantum potential. The results I'm going to present here today, they correspond to this last case, where we found analytical approximations for the quantum potential. And this doesn't solve the node problem, but it will solve the problem with the derivatives, because now we have an analytical expression for all that. So the results I wanted to show for this part, they correspond to the model, a toy one-dimensional model. We have a soft core Coulomb potential and time-dependent field. And we were interested at the time in studying the carrier envelope phase effects. So we had a sine square envelope, and we considered two different durations of the pulse. And for the short pulse, we can see how changing this carrier envelope phase parameter, you can dramatically change the shape of the field. And we wanted to study the asymmetry in the ionization by changing this carrier envelope phase parameter, and try to capture that with the trajectory description. So the first result I'm going to show corresponds to, so this is for 150, the value of the carrier envelope phase, and the idea is to show how we can capture the result from the wave packet propagation with the trajectory. So at the bottom are the results from standard wave packet method. This is a 1D problem, so we can use any standard wave packet method to solve this. And we can see how the trajectories, they capture the result from the standard wave packet propagation, we can obtain total ionization yields, and as the number of trajectories increases, we can show how it converges to the Gaussian, to the wave packet results. And then we move to understanding the carrier envelope phase effect. And the first thing I want to point out here is how by having a trajectory representation, we can clearly see the difference in the dynamics for the different carrier envelope phase parameters. This is shown in this figure on the left. So each panel corresponds to a different value of the carrier envelope phase parameter, and we can see how the dynamics changes, and we can already see the asymmetry in the photoionization, in the ionization of the electron. And on the right, we show the photoelectron spectra as a function of this carrier envelope phase parameter. At the top are the results for the left, but the electrons ionize to the left, at the bottom to the right. And we can see the first column corresponds to the wave packet method, and we can see how with the trajectory-based method, we can capture the main results from the standard wave packet propagation. So we apply this to several scenarios, and in general, we show that we have a fully quantum mechanical method that is wave function free, so there is no basis set or not grids, based entirely on trajectories. We apply this to study zero-point energy effects in both in harmonic or anharmonic potentials, to reproduce tunneling and transmission probabilities, and in particular in the example I show here today, to study the laser-driven electron dynamics and capture total ionization yields and CP effects like the left-right asymmetry in the photoelectron spectra. So these are the results I wanted to show about the Bohmian trajectories, illustrating how they can capture the quantum dynamics, but they have the main drawback that solving the equations of motion is very challenging numerically. Next, I'm going to move to path integral method for strong field ionization. This is work I did with Professor Carla Faria while I was at UCL. And I come back to the same initial picture, and I'm coming back to this now because now we will need to start making some assumptions about how the ionization takes place. So here we will be interested in the non-adiabatic regime for the ionization, where the Keldysh parameter is around 1. And in this case, we see in this the picture on the left corresponds to the ionization when the adiabatic ionization. In this case, the electron sees the barrier static while it's tunneling outside. But in this scenario, while the electron is being ionized, the barrier is moving. So we need to consider non-adiabatic effects in the ionization. And again, I'm going to look at one single active electron, and the possibility are that the electron is free with non-zero kinetic energy, where we have above threshold ionization, or the electron can be backscattered with a higher energy from the ion. The method we use in the group is the Coulomb corrected strong field approximation, and the idea is that I will not have time to give all the mathematical details, but the idea is that we use a path integral time slicing approach to calculate the transition probability of the electron to go from the ground state directly to the continuum state, neglecting all the interactions with the excited states, and the Coulomb interaction is included both during the ionization and in the continuum. And it can be shown that the transition probability for the CQSFA has this form. And we will focus on now this term here that has the contribution to the action. So we can separate the integral for the action in two parts, in two contributions. One contribution that comes from the ionization, that's what we call the tunneling type, tunneling contribution, and one contribution that comes from the propagation. So this contribution from the propagation is when the electron is in the continuum and is propagating freely, and this is in this region, we solve classical equations of motion for the ensemble of trajectories describing the electron dynamics. we can, the form of this action, once we do this splitting, is the following. So we have the action during the tunneling, that's also called the under the barrier action, and the action in the continuum. And we can see that in both cases, we have a contribution from the Coulomb potential, both during the tunneling and during the propagation time. So how was the CQSFA initially implemented, and what were the modifications we include? So initially, the CQSFA relied in assuming 4 types of orbits, and it was implemented as a boundary problem, meaning that we assume we knew the momentum of the photoelectron at the detector, and then we solve the problem backwards. And this had the advantage that was had a lower computational cost because only required 4 orbits. But it lacked of flexibility because we needed knowledge of the orbits before doing the dynamics, and the type of orbits will change if we change the type of the field, like if we change from a linearly polarized field to a circularly polarized field, for example. So we decided we wanted to do something more flexible for the CQSFA, and then we implemented a forward propagation method. And the idea, again, we have this action that we divide in the propagation part and the tunneling part, and we use the contribution during the tunneling under the barrier to derive an ionization rate. And this ionization rate then will give us information about the ionization probability of the electron, but at the same time, it will allow us to have like a probability distribution to find the initial conditions, then to propagate an ensemble of classical trajectories once the electron is in the continuum. The disadvantage now is that we need 10 to the 6, 10 to the 8 trajectories sampled from these ionization rates to get an accurate dynamics. So we are losing on the computational cost. But as you will see, we were missing some information by having some assumed pre-knowledge of these trajectories. And the final observable we want to obtain is the photoelectron momentum distribution in the detector. So we now solve equations of motion for the positional momentum of this ensemble of trajectories that describes the electron dynamics, and we beam the final momentum of the electrons of these trajectories at the detector. The model system we study is a hydrogen atom. We have, again, a linearly polarized field, and because of the symmetry, we can consider that the problem, we can solve it considering the direction parallel to the field, to the polarization of the field, and direction perpendicular to the field polarization. So the first results I wanted to show are to show how the non-adiabatic Coulomb-corrected ionization rates we analytically derive, and these density plots are shown as a function of the laser phase and the transverse momentum, and we can see the effect of including the Coulomb correction in the ionization rate. The rate elongates along the transverse momentum, and it narrows along the laser phase direction, and this will have an effect in the initial sampling of the trajectories, and of course it will have an effect in the final momentum distribution. So we then sample from this ionization rate, and we can run the dynamics, and we can obtain the photoelectron momentum distributions. On the left are the results from what we call the rate CQSFA, compared with the result from the TDSC obtained with QProp. And we can see, in general, a good agreement between the trajectory-based method and the TDSC calculations. And we observe that including the Coulomb corrections in the ionization rate, they introduce modifications in the interference patterns. And the best way to look at these modifications is to look at the single orbits momentum distributions. So I didn't mention that, but again, now we don't have, as in the initial formulation of the CQSFA, we don't have a pre-knowledge about the orbits. We run set of trajectories. We don't know how to classify them, but we can use at the end the same classification to find out if we have the type of orbit 1, 2, 3, and 4 that we had initially in the CQSFA. And these plots here, this corresponds to orbit 1. Just to give a bit of context, orbit 1 is the orbit that I can come back to the picture here, actually. So orbit 1 is an electron that goes, once it's ionized, it goes directly to the detector, and orbit 2, it's an electron that will follow these kind of orbits. And in general, this table will allows us to find this classification. But the main message I want to convey here is that including the Coulomb correction in the rate has an effect in the distribution of orbits 1 and 2. It elongates the momentum distribution along the transverse direction, which is the one that we have here in the perpendicular axis. But also, if we compare with the photoelectron momentum distribution corresponding to the initial implementation of the CQSFA, we can see that, but assuming knowledge about the types of orbits, we were missing a lot of information about the different types of orbits we can actually have in the dynamics. So CQSFA, the original implementation, was missing all this contribution to the photoelectron momentum distribution. And we can see the same for the other two types of orbits, that comparing with the CQSFA, that now we have additional orbits that were missing in the initial implementation. And also, if you look at the interference patterns, this is single orbits, and still we see an interference pattern because now we have different types of orbits that are classified under the umbrella of one particular type of orbit, as we had in the initial formulation of the CQSFA. So these are the results I wanted to show for this method. So we derive a non-adiabatic ionization rate with Coulomb corrections from the CQSFA transition probability. By having a trajectory mapping, we could perform a momentum mapping. We could understand the different contributions from the different trajectories to the final momentum distribution. And I wanted to say a few words comparing this path integral approach with the initial formulation I presented using Bohmian mechanics. So in the path integral approach, we include some quantum effects when we derive the ionization rate and we have the action in the continuum. But the equations of motion that these trajectories follow, once they are in the continuum, they follow the classical Newton equation of motion. And we need to introduce approximation to treat the tunneling step. While when we use Bohmian trajectories, we don't need to make any assumptions about the dynamics, not during the tunneling, not during the propagation in the continuum. But the problem is that Bohmian trajectories, they are very hard to solve numerically, so that's why we need to make compromises. But the question is, can we still improve the methods that we have if we use some of the information we know from the Bohmian formalism? And I have a few more minutes to go to the last part of the talk, where I wanted to talk about the work I'm doing now in... It's still okay, Carla?
Absolutely okay.
Yes.
Yes, don't worry. You have a lot of time.
Okay. So I want to talk about the work I'm doing now in Warwick with Gaussian wave packets. The Gaussian wave packets are very commonly used to do quantum dynamics. The standard form of these Gaussian wave packets is what we call the standard product Gaussian wave packets, where we have different ways of writing these Gaussian wave packets. In the ones I'm going to use here today, I'm going to consider that the width of the Gaussian wave packets is fixed, so will not change in time. And it's the same for all the basis functions I have. And then I can write my time-dependent wave function as a combination of expanded in these product Gaussian wave packets. And then to solve the quantum dynamics, we can use the time-dependent variational principle to obtain an equation of motion for the coefficients. And then we have different choices to propagate the parameters of the Gaussian wave packet, like the center and the momentum of the Gaussian wave packet. In our approach, we use the Ehrenfest-like equation. So the only quantum information that we have comes from the coefficients, because we obtain that from the time-dependent variational principle. But then the parameters of the Gaussian wave packet will move classically. And there is an intrinsic problem with these product Gaussian wave packets, and is the following. As we increase the number of degrees of freedom, if the volume in space that these Gaussian wave packets occupy goes to zero. So as f increases, as the number of degrees of freedom increases, the volume goes to zero. This means that if we want to treat high dimensional problems, by increasing the number of basis functions, we cannot improve the convergence. Another problem that they have is that this, in the equations of motion, I didn't show it here, but the overlap between these Gaussian wave packets, if they go to the unit matrix, then they will evolve independently. So it means that we have like an over-complete basis, and this triggers a lot of numerical problems when using Gaussian wave packets. And the energy convergence will depend on the completeness of the basis as well. So we wanted to deal with to improve some of these problems, and the main one that we wanted to deal with was how can we modify these basis functions. Instead of using standard products, can we use something different that can cover space better as we increase the number of degrees of freedom? And then we proposed two new strategies, two new variants of these Gaussian wave packets. One that we call stretch Gaussian wave packets, and the difference with the product Gaussian wave packets is in the width. Now we arbitrarily choose some of the Gaussian wave packets that will have a different width, will be a larger width compared to the other ones. This was one option, and the other option is the tethered Gaussian wave packets. And this one, it's not possible to write it mathematically, so I need to show it with a picture. So the idea is that now some of the degrees of freedom, some of the Gaussian wave packets, they will not evolve independently. So I will have like a seed Gaussian, which is this blue one here. And then when I introduce new Gaussian basis functions, I will introduce them tethered to the original one in some degrees of freedom. For example, if we look at the blue one here, we can see that the degree of freedom 1, which is the one along this axis, will be the same as the one corresponding to the blue. They share the same degree of freedom 1, but they are only free to move along degree of freedom 2. And for the red one, we have the opposite. So they will share the value of degree of freedom 2, and they will be only free to move along degree of freedom 1. So this effectively means, first, that we will ensure good overlap between the different Gaussian wave packets through the dynamics, and also we have an effective reduction in the dimensionality. So this will improve the convergence as we increase the number of degrees of freedom. We apply this for a model potential. As initial wave function, we use a product Gaussian wave packet, but then for the propagation, we use these two variants, and we compare with the results from the product Gaussian wave packets. And we compare our results with the ones from MCTDH, because we have access, as part of the Cosmos project, we collaborate with Graham at UCL, so we have access to quantics. And what we learn from that is that with the product Gaussian wave packets, this is the one shown on the top, as we increase the number of basis functions, we cannot really improve the convergence. Something similar happens for the stretch. However, for the tether, we can improve the convergence as we increase the number of basis functions. And this is better illustrated in this figure here on the left. So you can see the red one corresponds to the product. And we can see that as we increase from 200 to 250 basis functions, our convergence, the mean absolute error is not really improving. More or less the same we can see for the stretch, which is the purple line. But we can see for this one that the mean absolute error, this is the mean absolute error in the expectation value of degree of freedom 1, decreases as we increase the number of basis functions. Another improvement is related to the conservation of energy. I mentioned at the beginning that propagating these Gaussian wave packets, to be able to conserve the expectation value of the energy, we need to have a complete basis, which in general we we don't have. So we can see that as time goes, the energy increases while it should stay constant as this green line. And by using the tethered Gaussian wave packets, we see that the standard deviation around the energy decreases. So we are already also gaining, improving the energy conservation by introducing the tethered Gaussian wave packets. And I think I arrive to the end. So in this last part, I didn't show anything about with the fields, because the way these Gaussian wave packets are implemented, we don't know yet how to include the time-dependent field, but we have shown that by introducing a new type of Gaussian wave packets, we can improve the convergence for 6D and 8 dimensional systems. And things that we would like to think about is if we can improve the energy conservation with these tethered Gaussian wave packets, and what will be the best way of including the time-dependent fields. And there have been some work done for coherent states for electrons, but there are still many open questions of how can we use these Gaussian wave packets if we will want to treat the problems like the ones I showed at the beginning. Another question is like, can we capture entanglement with these semi-classical approaches? What do we need to do? And can we still learn something, even though we know it's hard to deal with the Bohmian equations, but can we still extract some information from there? And can we modify semi-classical methods in a way that we have a better description of quantum effects? And this will have an impact if we want to describe entanglement, for example. And something I'm personally interested in including quantum lights into these methods. And then I arrive at the end. I presented work here that I did during my PhD, during my work at UCL, and work I'm doing now. So I want to thank the group in both universities, and now I'm also part of the Cosmos project, which is a huge community working on quantum dynamics method that is involving many researchers from across the UK. And I want to thank you all for your attention. Thank you.
Thank you so much for this really nice talk. And other questions, comments? If you would like to ask anything, just raise your hands or write in the Q&A tab. Also, for those on YouTube, now we allow live chat for subscribers, so we are monitoring it. And in case you have any questions, do write there as well. People get quiet on Fridays, but they ask ultimately, right? Yeah, I don't know. Where is everybody? Hello? Okay, maybe I start. So, in your experience, let's say, if you would give a summary for the speaker or for the listener, what are the main advantages and disadvantages of the types of trajectories that you have been using? How would you summarize that?
Okay, that's hard to say. So I will personally, I really like Bohmian trajectories, but you cannot use them for multidimensional problems. But the main advantage is that they are quantum trajectories, so you can capture all the quantum effects. Path integral methods, I think they are very advantageous because they allow you to solve more complex problems, and you still get quantum effects included by the path integral methods. So I will say each method depends on what kind of problem you want to solve. I will say if you want to deal with this, laser-driven electron like time-dependent fields, doing that with Gaussian wave packets is not very straightforward. So I will say from the three methods I presented, path integrals will be the more suitable one right now. However, there is some work done with Gaussian wave packets, and yeah, there are still directions that will be possible to explore.
you very much. Now the questions are coming. First one from Menakshi Rana. Hi, Prof. My question is for trajectory-based quantum dynamics. The wave packet here is phase and density. And what is the length of the trajectory? Is there any orbit we can miss during the calculation of non-adiabatic couplings? Thank you for the talk.
Okay, let me see if I understand. So I suppose the first part, like wave packet here is phase and density, might be related to the initial Bohmian part where I described the wave function as a phase and an amplitude. So I will say you can have this answered for the wave function in terms of a probability density that will give you the square root of the square root of this probability density is the amplitude, and then you have phase. And what is the length of a trajectory? I'm not sure I understand what is the length of a trajectory means.
Can you elaborate on that? You can now, in principle, unmute yourself and ask more if you would like to. Could
Hi,
you
hi,
clarify?
Professor.
Hi, we're listening.
Uh, yeah, so for the length of trajectory, I was about to know like how long we can calculate or we can track the trajectory during the quantum dynamics. Like, is there any specific length or we can just go for any number?
Oh, okay, that's very good. Yes, because numerical error, for the Bohmian trajectories I presented, numerical error they will accumulate in time. So for this example I show, I think we run up to I think few femtoseconds. But yeah, if you go further away, like maybe I think for this one, it really, unfortunately, is problem dependent because some problems they are more challenging to solve numerically. So you will have more numerical errors accumulating during the dynamics, but
So
few
yeah,
femtoseconds.
okay.
Yeah.
Few femtoseconds, yeah.
Yes. Yes.
Because you said that the computational cost will be lessen with these methods. So I was hoping that we can go over the long trajectories for big system in less number of time. So that's why how I was
Ah, okay.
thinking.
But you mean you're talking about calculation time or how long
Yeah,
we can? Ah, okay,
yeah,
okay, okay, okay. Oh no, yes, definitely. The I did these calculations long ago, but for these 500, for example, if you want to do this 1D with 500 trajectories, yeah, maybe will be like 1 hour. So
okay.
I think that these methods they are still not really competitive with, MCTDH or things like that, because still with you can treat bigger problems with
And these trajectory based methods, this is just for 1D or 2D, like I'm just beginning with the MCTDH in my fifth year. So, yeah, these are like in 3D takes time, but
yes. So the one I presented for the Bohmian part, this was a 1D method because the answer, we needed to find an answer for the density to get some analytical expressions. And this only we had only one for 1D, then my PhD finished, so I couldn't do. But you can in principle get answered for 3D, but it will be very, very challenging to make it work. And the ones I presented for the path integral method, this was like we had a 2D problem because of the symmetry. We could solve it
yeah,
in 2D.
okay. And for the path integral one, you have shown the four orbits. Uh, during the non-adiabatic couplings. So I was thinking if we can have like miss any orbit during the calculations or during the calculation of non-adiabatic couplings, like any kind of crossing, maybe where the resonance is happening or something like that.
Okay, so first I want to clarify because it's the difference. So when I said non-adiabatic, it's not adiabatic couplings. It's not like you have different surfaces. So here, what we describe, we have one electron is in the ground state, so we have only one surface, and it goes directly to the continuum. It's different. It's not
Okay.
like when we have non-adiabatic couplings that you have different surfaces and you have transitions between them. we don't have
Okay.
this in this trajectory. So by non-adiabatic, I meant, it might be confusing, I know, because the non-adiabatic here, it meant like the ionization, during the ionization, the field was moving, so you cannot see the barrier static, but you don't have
Okay.
transitions between different potential energy surfaces.
Okay. Okay. Thank you. Thank you for the talk, Professor.
Thank you for your questions.
I'm muted, always forget this. We also have a message from Anika Ainu, and she would like to say that thank you so much for your wonderful talk, Dr. Lidice Cruz Rodriguez. I really enjoyed it, and it was very insightful to learn about different trajectory-based methods for quantum dynamics and the current challenges in the field, like adapting semi-classical methods to include more intrinsic quantum effects. This is a
Thank you.
comment.
Thank you.
Would anybody else like to ask questions? Come on. It's a good opportunity. Also on YouTube. Sometimes you have things on YouTube, and we have a lot of people there today. We had 10 people joining, which is good, but don't be shy. Ask questions. We're monitoring the live chat. So if you are a subscriber, you can definitely join the conversation too. And if you would like to ask anything, do use the opportunity from either way, from here or on YouTube, because these methods, they are ever present in many, many areas of physics, not only attoscience. So it is really good to know how you can explore them. And she has a great overview of many types of orbits. So do not feel embarrassed to ask. Do raise your hand. Nobody? Okay, let me see. Yeah, it seems people are not raising their hands and not posting on the subscription.
Friday afternoon, everyone is tired.
Sorry. Yeah, it's Friday, but you need to think we have people from everywhere. So people could ask. But I mean, what, in your opinion, is the future of these trajectories?
I think Gaussian wave packets, they are very, very, very popular, and they will, and path integrals method as well, because I presented things that people from completely different fields use, so it's very Bohmian mechanics. Unfortunately, I don't think there is much future as much as I like them. But I do think they can be used to interpret, even though if you manage to solve the quantum dynamics, like to get the wave function, you can, sometimes it's very difficult for the method that use, that the information you have at the end is only the wave packet, to get information about the dynamics, and you might be able to learn something from the Bohmian, but backwards, not to use them as solution tool.
No, I definitely agree, because people sometimes have the misconception that to do physics or chemistry or whatever is to solve a system with the biggest number of degrees of freedom that you can have. And there's also interpretation that needs to be done. I definitely agree with you. We also have a message from Nikolai Shvetsov-Chilovsky. Hi, Nikolai. Uh, Thank you for your very nice talk. My question is, don't you think that future semi-classical approaches in strong field, ultrafast, and attosecond physics lies in the combination of TDSE with classical trajectories, or TDFT as well? For example, we did such an attempt in the CT, so many acronyms, okay?
Yeah, quantum with quantum. I remember this paper from your.
SCTQSQI model in 2019. Yeah, we also have our acronyms. I
Yeah,
cannot
I,
remember.
I I totally agree with this point. Like, because I think I remember this paper from the uh, semi-classical two-step model with quantum information, and I think that that's a way to go. Like, if you have a mix, you have some time solution of the time-dependent Schrödinger equation, and then you translate this to classical trajectories. Yes, I agree.
Yeah, no,
Thank you
go
so much.
ahead. Go ahead. You can ask her personally if you would like to carry on.
No, thank you so much for the answer. Unfortunately, it also there are still problems with numerical scaling of this approach, which we called SCTS-QI, a semi-classical two-step model with quantum input. But I think that indeed we could all move into this direction in the future. Thank you.
Okay, are there questions, comments? I mean, we are getting there. And I'm pleased to see that people are joining and a lot of known people here as well. So far, so good. I think we don't have a lot of them. Also on YouTube, I'm monitoring here, but people normally they watch, but they don't ask when they're joining from YouTube.
It's good. It has been a nice discussion. Yeah.
Yes, I agree. Absolutely. Because these are methods that everybody uses either to interpret or to model things that you cannot model in a grid, or to, to have alternatives as well. So anyway, any questions? Okay, last chance, because I'm going to finish the streaming right now. So for those on YouTube, take good care of yourselves. We see you in 2 weeks. Last chance to ask questions.